Welcome back to another video. Today's topic is a very interesting one. We'll be talking about fans. Fans are very calculation heavy. There'll be some graphing involved, but we'll look at some concepts as well along the way. So without further ado, as usual, we're gonna start with the question. Table 1 below indicates values measured during the testing of a fan in a laboratory or a laboratory. Understanding is much more important than saying it right. So this is a table that we have. Volume flow rate, it's given, static pressure, input pressure, and power efficiency. Those are blank and we're given the data there. So we've labeled our columns A, B, C, D, E to just simplify our calculations going forward. We're also given there that the fan speed is 15 revs per second and the air density is 1.1 kilograms per cubic meters. Then the first question says you must calculate and then tabulate the information necessary to generate fan, air power, and electrical input power and efficiency curves for the fan. And the second part of the question says using that information generated above, we're going to plot the fan, air power, electrical power, and the efficiency curves. So we're going to do this step by step. There's going to be more questions here. So by the time we fully answer the whole question, we will have an understanding of what is happening. So what do we need to know? So the understanding of how we move air underground becomes very crucial at this point. So how do we move air from point A to point B underground? How do we do that? We create a pressure difference, right? So there must be a difference in barometric pressure, right? So this pressure difference is what we commonly call the pressure drop, right? So because of this pressure drop, the air will always move from the higher pressure to a lower pressure. So that's what we need to understand. So now there's a movement of air that is happening. We've created this pressure difference. There's a movement of air. Now remember, the medium through which we are moving this air also has a resistance. So in us creating a pressure, we need to ensure that we generate enough pressure so that we can overcome the resistance, right? So that we have a successful flow of air. Essentially, that's what ventilation is, right? We are trying to provide enough air to get rid of gases, provide breathable air to cool the area, and so on and so forth, right? So this pressure difference or this pressure drop, it can happen naturally and it can also happen mechanically. So naturally, we are talking of things like heat and altitude difference. They can induce a pressure drop, right? Giving us what we call natural ventilating pressure, or NVP. Okay, now we can also generate this pressure difference ourselves, right? Sometimes you may find that it's not sufficient. We need more pressure difference, right? We can do this by using mechanical devices or appliances or equipment called fans. So essentially that's what a fan does. It creates a pressure difference, right? And because it's mechanical, it allows us to adjust and ensure that we can create that sufficient pressure difference to overcome the resistance and ultimately get the air where it needs to go. So we have two types of fans that are used in mine ventilation. We've got the axial flow fans and we've got the centrifugal fans. Centrifugal, what matters is that you understand it. They differ in terms of their structure, as you can see, and application. So you would find axial flow fans having small applications. You find them in individual tunnels, in smaller excavations, and you'd find the centrifugal fans having larger applications, acting as booster fans or used as main ventilating fans. Okay, so I'm not gonna get into much into their structures, and that's a lot more theory. So we're gonna move to the characteristics, the important stuff that we need to understand to solve these questions. So before we select and install a fan for mine ventilation, we need to make sure that the fan can deliver the required quantity of air in an efficient and in an economic manner. Okay, so to do this, we obviously need to do some testing. So these fans are tested in a lab, and there are variables that we are recording during this test. This would be the pressure, this would be the quantity, and this would be the input electrical power, right? So we would graph these variables, and these graphs would then be called our fan characteristic curves or fan curves. So these are essential tools required to make the correct choice of the fan for a given mining situation. Let's talk numbers now. Let's calculate. Let's talk numbers. So first of all, we need to determine whether the fan is using its power efficiently or not. So we do this by calculating the air power delivered. Okay, so our air power will be WA is equals to PQ over 1,000. That's the equation that we use. Okay, so this 1,000 is just to help us get our power in kilowatt. So our WA is kilowatt. This is important to know. Our P is pascals, and then our Q is, well, obviously cubic meters per second, right? So this equation will only be valid, right, if your pressure does not exceed 2.5 kPa. If it does exceed that, then you need to look at the compressibility of air, right? So that's something else. So secondly, we look at the fan efficiency. The fan efficiency written by the symbol ATA. It's a Greek letter ATA, written as ETA but pronounced as ATA. So ATA fan is equals to WA P input, so this input power, times 100. These are the equations that we'll be using to calculate. So I think with this information we have enough for the first part of our question. Okay, so let's write our equations that we're going to be using. So for the air power, we've already established that our WA is equals to PQ over 1,000. But please note that in this case, the pressure was in pascals. The question gave us the pressure in kilopascals. So we need to retain that pascal. We do our conversion. Therefore now, our air power is going to be A times B there, multiplied by 1,000 to convert to pascals, divided by 1,000 to convert to kilowatts. So that's how that equation works. And secondly, we have the efficiency, which we also established that will be our air power, which is D over our what? Our input power, which is C. This is multiplied by 100. So that's our next equation. So we can do the first two, and I will fill in the rest of the table, and then we will meet in a second. Alright, so that's what we get. With that done, we can look at 1b, where we are required to graph the information that we've just calculated. So for the sake of time, I decided to hand draw the graph. So this is what everything looks like. So that's our pressure there. We've got our volumetric flow rate there. We've got our power and efficiency on the right hand side. That's how everything looks like. There's also a key there to indicate what each color means. feel free to use the scale. What's important there is the consistency of the scale to ensure that your graph appears in a way that we can interpret. Alright, so that's what we get. So essentially that's how we go about calculating and plotting our information. Now, a few things to note: this is information from the laboratory. Okay, we may need to make some adjustments when we take it underground. You might find that you have a different air density, or you have a different fan speed when you get to the underground environment, so we need to do adjustments. So in the next video we'll be looking at fan laws and how to do those adjustments, and we'll also be looking at how to interpret our graphs. What does this information mean? What do we need to know on the graph, and how to answer the questions on application of the information we've just calculated. See you all in the next one.